Hello class. So on this video, we're going to start on section 1.1. So we're actually going to go back all the way to the first section in the book. Now, this section is about direction fields. Now, I'm going to be doing an example here where I work the example by hand, but as I work the example, you're going to see why it's going to be important for us to be working with computing software instead of doing the examples in this section by hand. So please, if you haven't downloaded Mathematica yet, as I mentioned in the previous videos, make sure to download it as soon as possible. I know of at least one student that already downloaded the Mathematica and everything was fine. So if you need to download it and you haven't done it, go to the course homepage and then click on the link there that sends you to the instructions for how to download Mathematica. It should be pretty straightforward. If you have any problems, just let me know and I'm sure we can figure it out. Okay. So please do that. As I mentioned in the previous video, I'm going to send a message reminding you of doing this. And then either in the next homework or 2 homeworks from now, I'm going to ask you some problems where you have to use Mathematica. Okay. So that was an aside. Again, for this section, we're going to be in chapter 1.1. Now, this is going to be a generalization of what we did in the previous video. So in the previous videos, we were talking about phase portrait, right? Where given an autonomous differential equation, dy dx equals just an expression involving y's and constants, we were able to tell a lot of information about solutions without actually having to find them. Right? For example, we were able to tell if we know at least one point that lies in the solution, we knew on what region of the xy plane that solution had to stay in. Right? We knew whether the function was increasing or decreasing on that, or the solution was increasing or decreasing on that interval. It was a y-axis interval, or in that region, and we also knew the long-run behavior of this solution. Okay. Now, what we're going to do, like I said, is generalize this. How are we going to generalize it? We're going to look at an equation, differential equation of the form, not necessarily f of y, but something that looks like an expression involving x and y's. No restrictions here. It could be any expression involving x and y's. So what I'm going to do is I'm going to do basically what I did in the previous section, that I'm just going to work through an example. And then based on that example, you're going to see how this all works. Okay. So the goal is going to be the same as before. Given a differential equation of this form, what information can we get from solutions of this differential equation without actually having to find them? So let's start with an example. So what information can you determine? And I'm going to start with a simple differential equation. So what information can you determine given the differential equation dy dx equals 2 times x times y? So how are we going to work through this? It's going to basically be, kind of straightforward, but it's something that you haven't seen before. The idea is we're going to use this thing called a direction field. Now, this direction field is basically going to be, again, a plot. So I'm going to draw the xy plane. But now, what I'm going to do is, at each point, I'm going to draw a tangent line. So why is this going to work? Well, let's do this. For our purposes, this is f of xy. So let's try something. Let's plug in a value for x and a value for y into this differential equation. So let's plug in an ordered pair. So see what happens if we plug in the ordered pair. Let's do 1, 1 into f of xy. So what happens? So f of xy is the same as dy dx. I'm going to introduce some notation here. This is something you should have seen in Calc 1, and I'm going to expand it to this notation here. Whenever you have a function, in this case dy dx is given by 2 times x times y, and you want to evaluate you can use this notation here where you draw a vertical bar and then plug, and then on the bottom right, wherever you're evaluating at. So we're evaluating at 1, 1. At the point x equals 1, y equals 1. And you read this dy dx evaluated at 1, 1. So what is this going to be? Well, plug it into f of xy. It's going to be 2 times plug in x equals 1 times y equals 1, which is 2. Now think about what this is telling us. This is saying that the derivative of any function that satisfies this differential equation at the point 1, 1 has to be equal to 2. That is what this is saying, right? Remember that dy dx is a derivative of some unknown function that satisfies the differential equation. Right? So when we plug in the point 1, 1 and we get that this is equal to 2, we're saying that the derivative of this function, the point 1, 1 equals 2. If you remember also from Calc 1, let me write it as a recall here. Recall that whenever you have the derivative, evaluating at some point, let's say x naught, y naught, this is, or I guess I don't need this. So recall that the derivative of a function evaluated at a point is precisely the slope of the tangent line to the graph of y, at the point 0, 0. X naught, y naught, sorry. So as a quick example, I suppose you have a function, for example, let's do y equals x squared, looks something like this. So this is y equals x squared, right? So its derivative is 2x. So if we evaluate this at x equals 0, for example, what we get is the slope of the tangent line at x equals 0, which the slope of 0 means that it is a horizontal line. So we're going to do something like this. I'm going to draw, again, a plot. I'm going to draw the xy plane, and at each point, I'm going to graph a portion of the tangent line. Why? Because that tangent line that I draw, or that portion, is going to encompass this information. For example, when I draw the portion of the tangent line through the point 1, 1 in my plot, it's going to be a line with slope 2. And we're going to do that for a bunch of points. Okay? So let's try to do it. So let me draw a plot here. Have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So we already know, based on our work before, that at the point 1, 1, any solution is going to have slope 2. So what we're going to do is come here to the point 1, 1 and draw a tangent, just a portion of the tangent line, so a small strip of it that has slope 2. So slope 2, okay, so slope of 2 is going to look something like this. Okay. Now we're going to do this for more points. Okay, so let's try a couple more points. Let's say we evaluate the derivative. Let's do dy dx evaluated at 1, 2. What is this going to be? Going to your derivative, which is the same as f of xy, where we see an x, plug in 1, where we see a y, plug in 2. So it ends up being 4. So we go here to our plot, and at the point 1, 2, at the point 1, 2, again, we're going to plot just a small strip of the tangent line with slope 4. So slope 4 should look something like this, I believe. Okay. And we're going to do this for just a couple more. So let's see. Let's do dy dx evaluated at, say, 2, 1. Now just plug in x equals 2 and y equals 1 into f of x, y. So 2 times x equals 2 times y equals 1 is 4. So we go to our plot. And then at x, and then at the point, was it 2, 1? Right, so this is 2, 1, that's here. Again, we're going to draw a portion of the tangent line with slope 4. So something like that. Now let's see what happens on the x-axis. So let's go back. Let's say we plug in a point that lies on the x-axis. Notice that on the x-axis, the y-coordinate is 0, right, by definition. So let's say we plug in a point x0, comma 0, so y equals 0. Any point in the x-axis is going to have this form. Let's plug it into our differential equation. So 2 times x0 times 0, this is 0. That means that any point that lies on the x-axis is going to have, or any function solution that passes to the x-axis, at any point at that x-axis, it's going to have a slope of 0. Okay? So for example, at the point 0, 0, we draw a horizontal line. At the point 0, 1, 0, horizontal line, etc. Now, the same happens on the y-axis. Why? Because if we come here and we plug in a point on the y-axis, now if we are on the y-axis, the x-coordinate is 0, and then y can be anything. Plug this into the differential equation, we get 2 times 0 times y naught, and this is again 0, independent of what the y-coordinate is. That means that in our plot, any point on the y-axis is also going to have slope 0, so we draw a portion of a tangent line with slope 0. Again, that's a horizontal line. And our goal would be to fill this up as much as we can with points like this. So let me do one more. So we do the point 2, 2. Let's evaluate at 2, 2. So what is this going to be? 2 times x equals 2 times y equals 2. This is going to be 8. Let's go to our plot. Something with slope 8, so it's going to be very vertical. Just based on my sketch, right? It's going to be very vertical. Very vertical. Now, what's the point of doing this? Why are we doing all this? The reason is this. Let y be a solution to, let's say, to the differential equation. So dy dx equals 2 times x times y. That goes through the point, let's say, let's do 1, 1. Right, so all we know about this function or this solution is that it passes through this point. Now, even though we don't know what this function looks like, there are some things that we can do. We can actually draw a rough sketch of this function. Right? Why can we do this? Because we know how the slope is going to look like at each point of the tangent line. So basically what you're learning Calc 3 is that the tangent line kind of gives you a sketch of what the graph looks like. So if we go here again to this example, if I draw a bunch of tangent lines to the graph, you can see that if I were to erase the blue part, I would still have a rough idea of how the graph looks like, just from the tangent lines. So the same thing is what we're going to do here. I don't know what the function is exactly, but I have the tangent lines. So that gives me an idea of what the function is going to look like. So I know that this function is probably going to look something like, oh, okay, too vertical. This function is probably going to look something like this. Again, I'm just trying to follow the slopes that I'm seeing. Right? And then, for example, if we go here, the slope is starting to get closer and closer to 0. So this is a rough sketch of y equals f of x, this solution that passes through the point 1, 1. And that's the idea. Given that you know the derivative at each point, you can do this sketch of any solution by just plotting at each point a portion of the tangent line. And again, as you see in this example here, that gives you a rough sketch of what the function looks like, even though you don't know what the function is. So when we come here, we do this for as many points as we can. We draw these tangent lines, and that gives us an idea of what the graph looks, of what the function looks like, without actually having to find it. Now, as you see from this work, you can see why we want to do this using a computer algebra system. In this case, we're going to use Mathematica. Why? Because see how much work. The more points that we use, the more accurate the solutions are going to be. The fact that the fact that I have to calculate this derivative for all these points, well, it's going to be a lot of work. So just have a computer do it for you. So what we're going to do in Mathematica is we're going to have the computer do this plot for us without the solution, just the tangent lines. Right. So I'm going to show you code to easily do that. Once we have that, I'm actually going to plot a solution that goes to this point, and you'll see how the shape of the graph matches the shape of the tangent lines that we have, just like it happened in this example right here. So I'm going to do that in the next video.